Okay, couple of things. Actually, I will be recording these sessions. If it's not okay, then you can actually watch the recorded session instead afterwards. Otherwise, I try not to put any of your names there on the screen. So, but anyways, this is supposed to be a closed session, just the Metropolia students can join. And then let me show you my face just for fun for a few seconds. Oh, okay, cannot start video. Well, I'm not then showing my face. Can't show it right now. Wait a minute. I think it's just that. That setting. No, can't start the video. Great. Well, I'm here anyways. Let me start sharing the screen if that is working. Would somebody actually send me a message on chat window? Chat window that you hear and see me well, since I don't have any monitor other than you. Okay, excellent, good. So you should be seeing my screen here, which shows the embedded electronics workspace in OMA. Next time, try to be on waiting room before me. Otherwise, I have to just, you know, follow if there are anyone on the waiting room, and then little by little, one by one, getting you in. It takes some time, and it's also is a disturbance for me. Okay, so embedded electronics. You have had Anssi Ikonen's part. I think he told already about the project work, and then also the this Janne's part, which is the FPGA stuff. My part is digital signal processing. It's one very important part of the embedded electronics when we are talking about the devices with any intelligence and any sensors. You need to do some filtering, some data processing, and in this project actually you will be working on making a PI controller. The bravest ones can also try the PID controller, but anyways, I think the PI is the task minimum. There's already one question. Do we have any on-campus lessons? No, we don't. This is the directorate last week actually ruled that everything that can be organized online will be online. So this part can be easily organized online. Okay, and then you already saw one of my announcements about the DSP part last week. Let me open it. DSP some info. Read 26 times. Do I have any problem? No, 21 students online, so I would guess all of you have read this part. So review the first video. I assume you have done it. So there was basically some some general stuff about the course, and then basically you have installed the Octave on your computer. If you have not, then you are in a small, not a big one, but a small trouble, since we will be using Octave already today. Materials can be found from the obvious place, which is actually this OMA. And then these online sessions are on every Friday and at 11 o'clock, about 3 hours. We will have a break at the middle sometime. So practically there are two parts. First I will give you a brief introduction to these topics, theory part, so to speak, and after that we will have a short break, and then I will start showing how to solve the problems using Octave or MATLAB. Originally this course was designed for MATLAB, but since it's not available for free for your own computers, we will be using the Octave, which already have been tested plenty of times that you can actually do the exercises also online with the Octave. Okay, slideshows, all the material are available on OMA, and I'm recording all of these sessions. By the way, I'm recording it using a different tool. I'm using a Open Broadcast Studio to record, and so basically I'm not recording using this Zoom. I have found actually that that's not necessarily a good idea. And in addition to that, I have a monitor to see that the recording is going well. Okay, so let's see. How do I get? Okay, so let's go forward a little bit. Documents you can find under the DSP. Currently, they're the DSP part 0. That's the presentation. I think some of these links can be accessed only using Metropolia Google account. But what I have checked, basically, I think most of them will open with your also personal Google account, or just anonymously without any account at all. Then there will be, after each session, there will be also the video. So it's basically just video recording of what I'm showing up here. And then what else? Yeah, that's basically it. And again, reminder, please be online before me. It's 9 minutes late and I'm still letting people in from the waiting room. Okay, so next time.
Sorry.
Yes, that's fine. Okay, that's fine.
I'm Giuseppe. I think that it's not really easy to be really online before you because Zoom has some problems sometimes.
Yeah, but it's 9 minutes late already.
10 minutes before you, and I ended up accessing 5 minutes after you. So I don't know how much Zoom makes this feasible.
Okay, I try to keep. Well, this
probably
added,
if you give if you authorize people to get
these added features, safety features on the Zoom actually forced me to use the waiting room at the moment. So it wasn't that way earlier. It was just open link, but they have added some features. Okay, good. Going forward. Yeah, we have six topics. Starts from signals, ends to filter design. For your, basically we will have this fundamental part is part 1, 2, and 3, which is signals, systems, and responses. And after that, somewhere in the middle already, we have the system control. You will be starting actually doing the system control on your project, and I just watched the that nice video which explains what PI and PID control, or actually what is the control, video posted by Ansikon, and that was just marvelous, showing the what is it all about when you are talking about controlling systems. Okay, so a few weeks from now there will be system control lecture and some exercises on Octave. And then part 5 is about embedded systems, which basically means that when you start doing calculations using integer arithmetics, then you have some rounding errors. Okay, and that's basically it. And then at the end we also have some filter design. Practically speaking, system control is nothing more than a finite impulse response system, which is actually a one sort of filter. Anyhow, yeah, those are the material will be there on the documents. Then there are these 6 assignments. For example, today's assignment starts from here. Read the instructions. Instructions actually say how to work on the on each exercise. Wait a minute, that wasn't the I have a wrong link here, I think. Do I? Yeah, sorry about that. I have basically that's supposed to be a different link here. But you can actually find the exercise instructions on the beginning. Ah, wait a minute. Do I? Ha ha ha! Broken links. Sorry about that. I will fix those later. I will show just the instructions. You know, this is funny. I tested those links so many times, but it seems that I still have saved the wrong link here. Okay, but anyways, everything starts from here, that you will open the template for the exercises. I mean, you open the template and then start working through the exercises, but I will show you more about that one in about 1 hour. Okay, this part actually is 50 points in total, as any other part on this embedded electronics course. But we have 6. How to collect points is from the assignments. Each assignment is 8 points, except system control is 10 points. That's the most important for you, so it has a little bit more weight. That totals the 50 points in total. Okay, it's easy to gain points on exercises, but it's basically small things. The digital signal processing is a lot about details, which means that you can actually then start losing points on small details. And for that one, I have a collection of commonly made mistakes, basically on the instruction sheet, but I will fix the links later on today during your break. Okay, just there we go. No exams. No, there is no exams. Or actually there are 6 exams, home exams. Those exercises are kind of small exams. I haven't done any exams for more than 10 years. Actually, 18 years. I started thinking, okay, where do you go in, if you go to the real work, do you ever get that kind of exam situation on your current or your job? No, you won't, unless you are attending a paid course or something like that. Can you get a job as a DSP programmer? Maybe. Not necessarily in Finland, since they're in late 80s and early 90s. There was a lot of the engineers trained for digital signal processing. They are still working. Okay, and Nokia has downsized a bit since then. At least that digital signal processing part. So maybe not as a DSP programmer, but you may be actually working on a embedded systems project where you need that skill as a part of other engineering things. So yeah, it's a practical also for the say, it brings you one skill more. What else do we have? Somebody asked if MATLAB is okay. Yes, MATLAB is okay. Okay, yeah, good. Starts watching the chat window. Okay, good. So let's start and see if my first link actually works or not. Part 1. Yahoo, it works. A brief theory or brief summary on digital signal processing theory, and this is the first topic. It is digital signals, but do you have any general questions about this DSP part right now? Now is a good time to actually ask before I start going through the first theory lesson. Or you can also type them on the chat window. I will then just answer them whenever they appear. Okay, so digital signals. I have a funny picture like that. So basically, an example of what is on the digital signal properties. Good example is a voice recording process. So basically, you have a signal source, then you have some sort of the sensor, which in this case is a microphone. Then you have some digital signal processing equipment in between, and then you have somebody who interprets that. I know this is a stupid picture, but I made it myself. Okay, so the signal, what you do for the signal on that device, digital signal processing device. First, you need to have some the analog front end, meaning you probably have a very tiny signal, what you turn into electronic using that microphone, but that's millivolt level. And basically there are some artifacts. You need to also do some filtering. Then basically before it goes to digital, you have a sample hold circuitry there. And then you have the A to D conversion, although the sample hold and A to D usually are on the same circuit. So starting from a small signal, you amplify it, match the A to D converter input range. You get rid of the high frequency artifacts, usually with the low pass filter. Then after sample hold, okay, now you have basically samples in time. And after A to D conversion, you also quantize those levels. So basically, after the A to D converter, you have the samples in time, but also only using, say, 12-bit or 16-bit, 24-bit resolution. So it's basically integer number with quantized data size. Okay, so that is the digital signal at the end. Some of these ideas behind of the this kind of signal characterization. On the beginning, on the analog world, we have continuous time and continuous value signal. On sampled signal, we have a discrete time. So basically the signal is valid only on certain time steps, but still continuous value, meaning that it can be any value. And digital signal is discrete time and quantized value, either the nearest integer or floating or ceiling integer value. Okay, so those different characters. This course, first 5 exercises or 5 topics basically are considering the sampled signal. Oh, wait a minute. 4 topics. They are about sampled signal. So we are thinking of this data which can have any real value. On the 5th, which is the embedded systems things basically, then we also take a look at what happens when we quantize the values. There are some nasty effects actually. Okay, but anyways, most of the course is about discrete time but continuous value signals. Practically it means that it's floating point numbers can be used, but the signal itself is sampled, meaning tabularized. Okay, so let's focus on the sampled signals.
Could I ask a question?
Sure.
About the previous slide? So what were the red lines on the...
Red lines in here?
Yes.
Okay, these red lines means that they basically are discrete values. So basically it's valid only on these time steps, but it's constant value.
So,
So
what
it's
we
basically
see on the output of...
Yeah, so it basically freezes. Yeah, that would be shown on the output of the sample hold circuit. So it basically samples at that time step and then holds the value for the A to D conversion.
Okay, thanks.
Okay. All right, sampled signals. Signals actually almost in any case, all cases, we want to have a constant rate sampling, meaning that no arbitrary time sampling. Those are practically just data without meaning, or it's basically independent data, meaning that it's not really time series data. They are independent, marked and at certain times. You cannot do much of anything with that kind of arbitrary sampled data. There are some advanced methods for basically using that kind of data, but not recommended since we have plenty of, computing power usually on the systems, so we can actually just, sample with constant high enough rate to get all the needed information. Couple of terms. We have the sampling rate, Fs, usually marked as capital Fs, and then the sampling interval, meaning sampling time. That's basically the time difference between two subsequent samples, which is simply 1 over the sampling rate. So if we have, for example, 1000 samples per second sampling rate, then we have 1 millisecond sample time. Okay, you have probably heard that Shannon theorem before. So how many samples you need to get in order to reconstruct the signal later on. And that actually goes with the periodic signals, meaning sinusoid or something like that. You need to have at least 2 samples per original signal period in order to do that. If you have too long sampling interval, then basically this will lead to signal aliasing. I think you have had some time before in some math course, maybe engineering math course, about signal aliasing, but actually, it's here. So that blue line represents the analog signal, and then these red lines show the these periodic sampling points, sampling times. And their circles actually show what the sample would be. It's just the value of that blue line at that time. And then when you forget that blue one here and just connect these red circles, you can see actually that high frequency original signal also have a lower frequency alias if you sample it with too low sampling rate. Okay, yeah, that's certainly not a good thing to happen. A little bit also about the digital signal, because it was there. So basically it's just that in real life these A to D converted values are always quantized in value, meaning that they are simply there's some resolution, and the least significant bit is the quantization step size. So if we have a for example about 4 volt input range for A to D converter, and then you have a let's see, 12-bit A to D converter, which means about 4000 quantized step, then you can actually have the least significant bit value is about 1 millivolt. Okay, easy. Right, so one number which actually is quite important in digital signal processes is the signal to noise ratio. And here in particular we are talking about signal to quantization noise ratio. So there's a formula for it. That one actually tells you how many bits you need in order to achieve a certain dynamic range of the signal. So for example, in order to achieve 80 decibels, wait a minute, what is the weird x on the equation? Oh, x, that's the value. Oh, that's that weird x actually. The weird x, it's a mathematical marking usually used in literature. So practically, when you take a look at this previous continuous time, the bracket here, it's a capital X and brackets n. The brackets n in braces actually indicates that this is a sampled data. So it's a tabulated data. Practically that comes from programmer's point of view and how to mark the index on an array. Okay, and yeah, that's simply the when we have this normal parenthesis, that which this means actually it's a continuous value data. So basically this is still on analog world and this is on sampled world. It's a sample at sampling index times TS. Okay, so back to here. Yeah, quantized value. By the way, I'm using mostly I'm following these marking styles which are marked on some of these books I have mentioned. So the that Mitra's digital signal processing book, actually it uses this kind of markings. I don't remember totally how the that DSP guide, the internet book actually, network book actually uses the markings. But these are mathematical markings. I wouldn't be too worried about them. So basically this is how you mark the red half brackets here basically mean that it's floor value of whatever comes out of that one. Sampled data, floor value. Same in, say, a pseudo language here. Okay. Yeah, cool. Yeah, mathematics is actually cool. I don't hear anyone laughing. Okay, example. Audio signal. You know this probably from high school. Human ear can detect signals roughly from 20 Hz up to 20 kilohertz. You can still probably hear at 24 kilohertz. I'm not. I'm an old guy. And basically, which that already tells you you must have at least 40 kilohertz sampling rate minimum for good audio recording. Okay, and for some reason, when you're talking about CD quality pulse code modulated signal, it has 44.1 kilohertz sampling rate. Fine. Somebody has decided, okay, we shall use that 44.1. I think that was the Sound Blaster, the original Sound Blaster, which then afterwards became a industry standard on sampling. So that's enough for showing signals up to 20 kilohertz plus. Remember, before I showed you the low pass filter. Okay, the low pass filter is analog filter before the sampling. Basically, you need also some the safety margin for that high pass, low pass filter, so that it filters out these spurious, very high frequency stuff, and still leave that 20 kilohertz information bandwidth there without any change. Okay, then listening music. Sound pressure level in range of 20 to 100 dB. 20 dB the audio means dropping a pin to the floor 10 meters away. So that's the smallest amount of audio what you can listen. And then 100 dB is already so that it will damage your ear if you keep it at 100 dB. So the dynamic range is 80 decibels. And when you take a look at the signal to quantization noise ratio, you need more than 13 bits resolution for recording with the high enough quality. Okay, and what basically is not accidental is that CD quality, pulse code modulated signal, has 16-bit resolution, 2 bytes, one 16-bit word. Okay, that's easy. It's easy to, you know, save on computer memory. And of course, you need a few more bits always in order to avoid the overloading or something like that, overdriving the signal. Okay, so audio signal, when we are talking about CD quality, standard PCM signal, 44.1 kHz sampling rate and 16-bit resolution. So Shannon theorem in reality, what it means, and then the other one is how many bits you need. It comes from the how small signals you want to actually measure. Okay. Now let's go to the digital basic digital signals, fundamental signals. The first one is the unit impulse, which is called the discrete Dirac delta function, meaning that it is valid only on those index points, also negative indexes, from -3 to 5 on this picture. Okay, those are index points. They are not tied into any particular time yet. What ties them into the time is the sampling rate or sample time. So, for example, on that 1 kilohertz sampling rate, this would be the time 0, 1 millisecond, 2 millisecond, 3 millisecond, and so forth. Okay, and Dirac's delta is simply 0, everything else except at the 0 index, then it gets value 1. Compared to Dirac's delta, which is the mathematical tool for doing stuff in continuous time space. Okay, it's a bit different in sense that actually it's impossible to use other than pen and paper. At 0 point it gets infinity value, such that when you integrate it from -infinity to infinity, you get total energy of 1. Okay, so that's the original Dirac's delta, which is a mathematical tool for pen and paper, while the discrete Dirac's delta function is a practical tool for these the discrete time signals. Another one, basic signal, is the unit step, also called at Heaviside. I think your math teacher actually uses this name Heaviside for that function, which is kind of Heaviside since it goes heavy on the right side, something like that. Okay, so Heaviside, again, discrete time signal shown as a bracket, which is a sampled Heaviside function. Sampled analog Heaviside function. So practically, if the index is negative, then there's on this Heaviside or unit step is 0 and bigger n, basically the value is 1. Simple. It's a sampled Heaviside function. Okay. What is the relationship between the delta and Heaviside mu. Well, you can get a delta function by taking this one and take a delayed function, meaning that it would start at 0.1 and subtract those from each other. So basically you will cancel the rest of that signal. Okay. Yeah, that's how you get it. Actually, this has one good application, but I will show you that later. Okay, and then on the other hand, if you take the no, that's not correct. Sorry, it's supposed to be k from 0 to infinity. You can also get the Heaviside by taking every single delta function with delays, the positive delays until the end of the word. Okay, not that useful. Oops. Then this delta function versus x of n sampled data. Actually, this is one way of constructing a signal or thinking of a signal. Signal is basically just a supercomposition of the individual signal points. Okay, so you can construct any signal by taking each of those time delayed parts and adding them together. Mathematically, it goes like that. Okay, more stuff. Periodic signals. Periodic signals. Analog signal or continuous time signal is periodic if you can find a constant time period such that you get exactly the same values in any time point. In here, basically you can get the same value of this that point also at 0.2, also at 0.3 and 0.4, and yes, and 0 here. So basically, if you can find such a constant time period that one is true, then basically that's periodic signal. Okay, but you already probably have had lots enough of practice on that on mathematics course sometime. Sampled signal, everything changes. In principle, sampled signal is never periodic, or in practice it's not ever periodic, because it's really hard to get exactly synchronized clocks. If you have two clocks and you don't have any physical synchronization between those clocks, at some point, at some time, they will lose the synchronization, and basically after that, if one is measuring and one is sending, then you lose the periodicity. But anyways, it's still that's such a good to remember that if you have a periodic signal in real life, there will be some artifacts when you do the sampling. So basically, usually you can find the periodicity only in pen and paper, not in real life. But still, the definition is quite the same as for the these continuous time signals. Okay, and here's an example that, okay, when you start here, similarly, or actually is it the same? It's exactly the same signal as previous, but when you start sampling it, you would need lots of good luck to get exactly the same or synchronized sampling with the fundamental frequency of that signal. As you can see, it's more or less arbitrary values what you can find from the sample signal. Okay. Okay, this far we have had fun with the signals in time space. A little bit more. Let's move it a little bit, not really complex. It's different. If we have periodic signal, those can be then presented as sum of frequency components. So you have probably already on mathematics class, you have had this cosine and sine series and Fourier transformation and that kind of stuff, or Fourier series. Okay. Just a reminder, basically, that any signal can be analyzed also in frequency space. It's just different space. It's equally untouchable than this time space. You cannot definitely do thinking on in 1 millisecond sampling rate. So basically it's the sampling frequency, high sampling frequency makes even the time space a bit awkward for human brain, I would say. Frequency space is as awkward as the time space as a kind of phenomenon. So nothing to worry about the frequency space then. It is as confusing as the time space. But you should be okay. You're electronic students, so you have done these border diagrams and that kind of stuff, so you know the frequency space already. Random signals. Random signal has unpredictable values, which can be also measured statistical or spectral properties. And some examples where to get the random signals. Practically everything on a digital signal processing point of view, all the interesting signals are random, just like human voice. Although it has a meaning, but the signal itself is more or less random. It has some statistical and spectral properties that human ear detects and your brain understands, hopefully. I'm not sure about my brain though. But anyways, the some examples, for example, wind noise in microphone. Small scale turbulence or mechanical structures causes wind noise, and yeah, that's unpredictable values. They are, but it doesn't say that it will be, you know, something that you cannot deal with. There are some methods to decrease the amount of wind noise in microphones. You know it. My first cellular phone, I got my first cellular phone on 1996, and you couldn't speak to it if it was windy. Outside, no way. Now, no problem. If it doesn't work well on windy situation, then you probably just change the phone to a better one. So there are some filtering you can do for that one. But then there are a couple of things that you cannot do anything, you just have to live with them and minimize the effects. One is shot noise in electronics, current carriers, electrons or holes, have constant value. So quantized charge. And there's a formula for that one. So shot noise. If you have very small current, then basically at some point it resembles like gunshots. So very low current, it basically you just or drop a bean to a can. Those are sort of like snap, snap, snap. Johnson noise, which is basically random thermal movement of charge carriers in conductors. Physics, yeah. What you can do with that one, not much of anything other than minimize the effect. So basically, if you have any charge carriers in any temperature other than absolute zero, then you would have that thermal noise. Okay, random signal nature. A couple of different distributions on small numbers, natural processes, especially on these quantized or in time signals, meaning sampled signals, or quantized in value signals. It's Poisson distribution. Okay. And basically there's the number theory that tells you, okay, if you take enough of samples, then everything goes to normal distribution. Something like that. Okay, that's what they look like, Poisson distribution, and they normally distribute random numbers, but usually you are looking at histogram. So do a statistical analysis to see how these values are spread. So Poisson distribution doesn't have any negative values. So basically those are the rolling dice events kind of things, or actually no, not like that. Those are quantized events. But that more, more popular model would be to use the normally distributed numbers. Okay. And yeah, enough of samples, you can start seeing the on the histogram this bell-shaped curve. Okay. Good. Okay. So that was about the randomness, random signals. Correlation. Cross correlation. This is actually something that requires a computer to show it. It's basically cross correlation measures the similarity between two signals. And practically it's made by taking one signal and those two signals and start time shifting them. So basically, if you have a similar feature on the signal, then basically it will be magnified by a factor of a lot on that cross correlation calculations. And the highest peak position would actually indicate what is the time difference between those the signals. Okay, but more on that one later on. Or do I have the? Oh yes, I have actually the a example there. Autocorrelation measures the self-similarity, meaning that you will be correlate the signal to itself, meaning that actually you time shift the signal and multiply each point to the original one to find if there are similar features on that one. Oh, similar, why does it need similarity? Okay, it measures the similarity. The next example is actually a nice example of that one. So correlation basically measures the similarity. And then just a reminder here, I think this already have been taught by some math teacher. One application for Fourier transform is to calculate the cross correlation or correlation. But anyways, you get more into it in the laboratories or exercises. Okay, correlation example. Radar, practically any radar. You send a pulse. Let's see if I can actually do a annotation tool here. Okay, so practically acoustic radar. Let's see, do I have, no, it's not here. I try to draw it here. Okay, I should have a drawing pad here. But anyways, so we have a loudspeaker. Oh, this will be so crappy picture. Which sends a sound pulse. There. And then we have an object. That's me. Yeah, definitely me. And basically what happens, of course, the signal will be reflected, or part of that signal will be reflected from my face to microphone. Okay, what the signal would look like on the microphone. Wow. So first it shows that original signal here. That was the pulse what was sent. And then silence. And after a while, the reflection comes back and you see similar but smaller amplitude signal on a microphone. Okay, how do you measure basically the traveling time between the signal and when it reaches back here? So that's the traveling time, t. How do you measure it? You will calculate the cross correlation. This line here, that red and green part, actually they are on the same signal. When you calculate the cross correlation function, C, F, yeah, I need a drawing pad. Yes, these meetings are recorded. I'm not using the this Zoom recording. I'm using external. I'm using a different the recording device. So I have the Open Broadcast Studio. Much better recordings, more reliable. But thanks for knowing. Sometimes I forget to turn the recording on. All right, so the cross correlation function actually would show a peak at the middle, which comes from time lag 0. Remember, that was the correlation actually calculates, keeps that signal on one constant and then multiplies it with the same signal with different time the differences. Okay. There you have always at the zero time lag you have the maximum correlation, since you are correlating it exactly with the same signal. But then basically this one with his similarity on the signal, it will show up here and also here. Its autocorrelation function is always, you know, symmetric. So basically that same time difference in this cross correlation picture. Okay, let me tweak it a little bit. This would show another correlation peak here. So basically you can measure the how long it took for that signal to go to my face and back as a time difference. That they did out of the zero region, that maximum correlation peak there actually shows that there is similarity to that signal, and also the way it happens, that's the maximum peak place here, and that gives you the time difference. So that's the fundamental working principle for any radar, not just the acoustic radar, meaning solder or depth finder on a boat, or actually also the same principle as in these radio wave radars. They are sending a recognizable radio burst, and then it gets reflected back, and it's fundamentally it's a correlation, the cross correlation or the autocorrelation of the signal which is measured, and that gives you the picture, so to speak. It's just a time series of cross correlation pictures. Okay, that kind of, ooh, should I clear the annotation eraser? Oops, clear. There we go. Right, that was the correlation. Another which is quite close to the correlation is the convolution. Convolution between two signals, it's defined quite the same way as the correlation. Only the sign of this time lag is changing because of the mathematics. So practically what this one is the time-space calculation of multiplication in frequency space. So if you have a frequency space, you design a filter. Like in Bode diagram, you have the frequency response of a filter. And you want to multiply your signal in frequency space with that filter. The convolution actually is a calculation in time space for that frequency space multiplication. But more on that on the week 6, or the study week 6. All right. I told you already about the signal to quantization noise ratio, but overall the signal to noise ratio, how it's defined. So that's the definition. It's 10 times 10 base log of signal power divided by the noise power. Simple as that. If the signal and noise variances are known, so practically noise variance, the variance of anything is directly proportional to the power. Okay. So basically signal power can be then also calculated from the variance of the signal, and then noise power is calculated from the variance of the that noise path. That's quite practical to remember when you are simulating these noisy signal samples. So if you have a requirement for a simulated signal to have a certain signal to noise ratio, you just first generate this signal and then add certain the correct amount of noise to that signal to achieve this required signal to noise ratio. Okay, so 10 times log of 10 power divided power. Of course, when you have signal amplitude, then you have the 20 times log. But you will be practicing it. Okay, spectrum analysis. Power spectrum. Power spectrum tells the power distribution of the signal, how it's distributed by the signal frequency. So this is very practical tool for finding out which part of the signal is actual information and which part is the noise. And it can be calculated by Fourier transforming the signal. And we will practice this one at some point. Example. I had a sampling rate of 1000 and I actually sampled a 50 Hertz signal with that sampling rate. So that's my that's what it looks like in mathematics. Okay, I have the signal is sine of 2 pi 50 Hertz times t, where the t is now sampled, meaning n times ts, which is n divided by fs. Okay, that gives the sinusoid. What I have here is a multiplication with window function. In order to do any calculations, I need to limit the number of points on my sample. So practically I need to use some sort of limiting window, meaning, well, window limits what you see, right? So let me take the annotation tool and try to be a little bit more. So if we have a a signal like that going on from infinity to minus infinity, I want only that part, analyze only one part. I cannot do the whole part. Basically, it means that I need to multiply mathematically this signal with a window. That's the window, rectangular window in this case. Okay, so yeah, windowing basically brings some effects, and when you think of 50 Hertz signal, I should see only one single point on that 50 Hertz frequency on my figure here, but due to this window effect, you get this spreading of the spectrum. Okay, so all this the spectrum analysis, you also need some interpretation of the watts. So when you are seeing a single frequency with envelopes, you need to figure out if those envelopes actually are real sidebands of a spectrum, or are they caused by this sampling. Okay. Another thing about the spectrum analysis, or a tool, a really nice and useful tool is to calculate a spectrogram, which is a time series of spectra of subsampled data, meaning you have that, what I draw previous slides. Okay, let's see if I can do any better annotation. I really need a drawing pad here. I heard that, I noticed the Heikki Valmu is really good at drawing things on this Zoom window. So practically what this one is, we have that signal, like that. And then we take a single section from here to there, for example. So, and represent the spectrum as one of those time lines here, for example here. Oops. Color coded so that there is the at certain time you show the spectrum, single spectrum, and next you will move that sample frame a bit and calculate the spectrum again, and that's the next one. So what comes out at the spectrogram, you have a time series of how the power of the signal is changing by the frequency, different frequency components. Okay. And here I have the example of having a chirp signal. Well, it continues that way. This is 2-second sample, but this subsample would have been only 0.3 seconds. Okay, maybe the first line here. And so basically this spectrogram shows immediately for me that, okay, it's a signal which starts from 0 frequency, and at the 2 minutes the frequency is 500. So that's a chirp. It changes frequency by the time. There. It's just a representation of this basically the frequency components of that signal in time. Okay. All right. So just about the time to have a break. If you want to, there is a questions for self-study. Maybe it's still there. I think it's still there. If you want to see if you understood the fundamentals, go ahead. I think you can just go and click those and you will see the results how you did. I'm not watching what you answered there. It's for yourself. It's a self-study. Okay, any questions? Subsampling mean windowing. Yes, subsampling means exactly that one. More questions? Okay. If not, if you logged in as with your Metropolia account, then you can actually also somehow click somewhere to give me feedback directly to this document using comments tool if you wish. I have been improving this little by little. It still needs some work, but I really appreciate if you point out some things. Maybe about pointing out that there could be more illustrations so that I don't need to start scribbling with the annotation tool without that drawing pad. Okay, and we will have about 15 minutes break now, and we'll be back at 12:30. Continues at 12:30 sharp. Infinity to infinity passage. Yes, good. I will fix that one too at some point. Great. But now I'm turning off the sharing and caring. You can give me feedback also in this chat window. I keep the chat open, but try to also concentrate on fixing those couple of things. So I will turn off my microphone though. So continues at 12:30.